Wow. Wow. Sup dudes. It's about analytical engineering. I am ripping off a book here. Of course. What is data ingestion? Who know? You know. To access your data, combine it with other sources, enrich it, or share it across an organization. You will first need to get that data into your data platform. This is the process we call data ingestion. Data ingestion equals how you get and transmit your data, accessing and distributing data through a device, software or a platform. Data analytics puts the data into the database context. So when it talks about data in general, it most likely refers to it as something that is either taken out of an existing database, extraction, or something that is going to added to it as new data, insertion. You can probably load data both in and out of databases. Most of the time you want to validate or test the data in some way to prevent your databases from being populated with useless junk that does not belong there. As an analyst, you care about answering questions from business stakeholders about the usage of that application. 1. Trigger. Here is an outline for collecting data for your sales platform to use, as in the things and the aspects to consider. 1. Trigger. How and when does the pipeline start? 2. Connection. What are the requirements for connecting the source system or database to the target or destination? 3. State management. How do you keep track of what has and has not changed since your last ingestion? How do you handle changes to the data over time? 4. Data extraction. What is the actual process of extracting data? Do you query a database, access an API, or just read files? 5. Transformations. Is there any filtering, cleaning, reshaping, deduplication, or similar process that you need to apply to be able to move your data from the source to the destination? 6. Validation and data quality. How sure do you want to be that the data is correct? What kind of guarantees do you want to enforce and what kind of anomalies are you willing to accept? 7. Loading. Where do you store the data that you captured? How do you handle connecting and adjusting to your destination system? 8. Archiving and retention. How long should you store or keep the data you just captured? How do you handle expired data? In addition to these steps, there are 3 big overarching topics that are relevant to the entire pipeline. Scalability and resilience. As the data grows over time, are you still able to handle the additional load? What is the fault tolerance of the entire pipeline and how often does it retry before giving up? Monitoring, logging, and alerting. How do you make sure you are aware and able to debug when there is an issue anywhere in the ingestion process? Governance. What kind of agreements do you have with both the source data provider as well as the destination owner? Are there any legal requirements you need to consider when handling this data? Data warehouses are essential for business intelligence, BI, and data-informed decisions. Organizations can effectively use vast amounts of information by consolidating and combining multiple data sources. If an analyst runs a complex query on an operational database at an e-commerce site to analyze sales data, it could slow down primary operations, such as processing current customer orders. This might cause transaction delays or affect the user experience negatively, leading to customer dissatisfaction and lost sales. The root of this inefficiency is the row-based storage used by these databases, which is great for transactional data but not mass data analysis. In comparison, data warehouses use columnar storage, which is more efficient for analysis. This is because it's similar to selecting only the relevant columns in a spreadsheet, bypassing the unnecessary data in other columns. Benefits of cloud versus on-premises data warehouses. When evaluating data storage solutions, it's crucial to understand various features and how they differ between cloud data warehouses and on-premises data warehouses. Scalability. Scalability determines a data warehouse's ability to adapt to increasing data and user demands. CDWHs shine in this regard, with their virtually unlimited scalability, allowing resource adjustments on the fly. However, this flexibility can lead to complexities in resource management and cost inefficiencies. In contrast, on-premises data warehouses offer stable physical infrastructure scaling but face inherent limitations in physical capacity, demanding substantial investments for expansion. Performance and speed. Performance and speed are at the heart of efficient data processing. Cloud solutions excel here, leveraging the latest technologies for high performance, though they may face latency issues during extensive data transfers. On-premises solutions offer direct control over performance, but boosting their capabilities often means costly hardware upgrades. Accessibility and collaboration. In today's distributed work environment, accessibility and collaboration are vital. Cloud-based warehouses provide effortless internet access, fostering team collaboration, albeit reliant on stable internet connectivity. On-premises warehouses, while offering high security, often require additional infrastructure for remote access, adding complexity to IT operations. Security and compliance. Security and compliance are paramount in protecting sensitive data. Cloud providers bring robust security features and manage compliance, but shared resources can raise concerns. On-premises warehouses allow tailored security measures but demand significant resource allocation for managing these aspects. Innovation and features. Staying ahead with technology is another crucial factor. Cloud providers continuously introduce cutting-edge features and analytics tools, albeit with a risk of dependency on their technologies. On-premises systems allow custom solutions but lag in adopting new technologies due to manual update processes. Disaster recovery. Effective disaster recovery strategies are essential for business continuity. Cloud services excel with their comprehensive, multi-region backup solutions but depend on the provider's capabilities. On-premises systems offer physical control over backups but are more vulnerable to localized disasters and require heavy investment in backup infrastructure. Cost predictability. Cost predictability is crucial for budget management. The cloud's pay-as-you-go model suits variable workloads but can lead to unpredictable costs. On-premises solutions, while demanding high initial and maintenance costs, provide more predictable financial planning due to their fixed infrastructure investments. CDWH means Cloud Data Warehouse. Data analysts dive into data to find patterns, make comparisons, and extract meaningful insights that inform business decisions. They take on the following activities: creating dashboards to visualize sales performance, running SQL queries to answer business questions, developing reports to track marketing campaign effectiveness, analyzing customer feedback to identify areas of improvement, comparing historical and current data to spot trends. The skill set required for this role has the following requirements: efficient querying capabilities, support for various data visualization tools, ability to handle large data sets seamlessly. Data engineers build and maintain the data pipelines. They ensure data flows smoothly from the source to the warehouse and is stored in a clean, usable format. They take on the following activities: designing and building data ingestion pipelines, ensuring data quality and integrity as it is collected and stored, optimizing data storage for efficient retrieval. Data engineers build and maintain the data pipelines. They ensure data flows smoothly from the source to the warehouse and is stored in a clean, usable format. They take on the following activities: designing and building data ingestion pipelines, ensuring data quality and integrity as it is collected and stored, optimizing data storage for efficient retrieval, implementing data transformations to ensure consistency, managing and monitoring data ingestion and storage systems. The skill set requirements are as follows: robust and flexible data ingestion and storage solutions, tools for monitoring and managing data quality, capabilities for data transformation and optimization. Analytics engineers bridge the gap between data engineering and analysis. They are instrumental in creating common data sets, documenting and testing data processes, and focusing on data quality to ensure its reliability and utility across all user groups. Their day-to-day activities include the following: developing and maintaining accessible and understandable data models for analysis, facilitating collaboration between analysts, scientists, and engineers for insightful data usage, enhancing data quality through testing and validation of data, working together with data engineers to optimize data warehouse performance. The role requires the following skills: support for collaborative development with analysts and data engineers, Data governance capabilities to enforce policies and ensure data access for the right users. Integrations with data modeling and ELT tooling, ELT equals extraction, loading and transforming. Data scientists. Data scientists use statistical, mathematical, and computational methods to generate insights. They undertake the following activities on a typical workday. Develop machine learning models to predict future sales. Run complex statistical analysis to identify market trends. Create algorithms to enhance customer recommendations. Analyze large data sets to derive actionable insights. Experiment with different modeling techniques to improve prediction accuracy. The job role requires the following: support for advanced analytics and machine learning frameworks. High-performance computing resources for running complex models. Scalable storage to handle growing data sets. Business users. Business users seek insights that help them make informed decisions. They rely on views and reports generated from the data stored in the CDWH. A business user performs the following activities: reviews monthly sales reports to track performance. Accesses dashboards to get a snapshot of customer satisfaction. Analyzes market trends reports to plan future strategies. Compares current performance metrics with past data. Reviews financial reports to make budgetary decisions. Here are the requirements for this role: intuitive and user-friendly interfaces. Access to simplified views and easy-to-understand reports. Reliable data quality to ensure accurate insights. Platform administrators. Platform administrators ensure the system runs smoothly, securely, and is up to date. They undertake the following activities in this role: manage user access and permissions. Monitor system performance and address issues. Ensure data security and compliance with regulations. Implement updates and patches to the CDWH software. Coordinate with other IT teams for system integrations. The requirements for this role are as follows: comprehensive administrative tools for managing users and security. Monitoring and alerting capabilities to track system health. Support for integration with other IT systems and platforms. Query engine. Although the query engine could be considered part of the computing resources of the data warehouse, it is a critical enough component to warrant its own section. It is responsible for interpreting, planning, and executing the SQL queries analysts and applications execute. The engine is pivotal to determining the efficiency and speed with which data can be accessed, analyzed, and turned into actionable insights. Some key features of a query engine are as follows. SQL query processing. At its core, the query engine processes SQL queries. This involves parsing the query to understand its structure, planning the best execution strategy, such as which indices to use and in what order to join tables, and executing the plan to retrieve or manipulate the data. Optimized for distributed systems. Modern query engines and CDWHs are optimized for distributed computing environments. They break down complex queries into smaller tasks that can be executed in parallel across multiple nodes in the data warehouse cluster. This parallel processing enables handling large datasets and complex analytical queries more efficiently than traditional single-node databases. Smart caching and indexing. Advanced query engines employ intelligent caching mechanisms and indexing strategies to speed up query processing. By storing frequently accessed data in faster storage mediums and maintaining efficient indices, query engines can significantly reduce the time it takes to fetch and analyze data. Cost-based query optimization. Cost-based optimization is a feature where the query engine estimates the resources needed for different query execution plans and chooses the most efficient one. This optimization considers factors such as data distribution, available indices, and the current system load, aiming to minimize the time and computational resources required for executing a query. Support for complex analytics. The query engine is designed to support various analytical functions, including aggregations, joins, window functions, and machine learning algorithms. This capability lets users perform sophisticated data analysis directly within the data warehouse. Security. Security is a cornerstone in the effectiveness of CDWHs. This includes a range of measures designed to safeguard access and protect stored data. Access control. Comprehensive access control is essential. This involves not only single sign-on, SSO, capabilities, which integrate an organization's existing account management systems with the cloud platform, but also the implementation of robust network security settings. These settings can restrict access to authorized networks, such as a company's internal network, enhancing the security perimeter. Encryption. Data encryption is pivotal in securing data, both at rest and during transit. Advanced encryption standards such as EASE are typically employed, with cloud vendors offering managed and client-managed encryption key options. The choice between these options affects how encryption keys are controlled and can affect security and compliance. Compliance and regulations. CDWHs must adhere to industry-specific regulations and standards, such as GDPR for data privacy in the EU or HIPAA for healthcare data in the USA. Compliance is supported through various security features and regular audits. It is critical to check with your company's regulatory guidelines to see what boxes the CDWH needs to tick. Zero Trust Architecture. Adopting a Zero Trust architecture is becoming a norm in cloud data warehousing. This security model operates on the principle of never trust, always verify, ensuring continuous validation of all users and devices accessing the data warehouse. At its core, Zero Trust architecture operates under the assumption that no user or device, whether inside or outside the network, should be automatically trusted. Central to Zero Trust is the concept of least privilege access. Users are granted the minimum level of access necessary to perform their tasks to limit potential damage from a breach. Managed ingestion, this is responsible for the L in ELT. It helps to streamline data extraction and ingestion through third-party managed software applications. Data warehouse/lakehouse, these are cloud-based systems used to store large volumes of data. Transformation, this is what the T in ELT stands for. Transformations help in data cleaning and preparation to meet business intelligence needs. Orchestration, orchestration helps in setting up specific tasks to run automatically at a particular event. As an example, an orchestration tool can be paired up with dbt Core for scheduled transformation. Self-service layer, in this block, reports and analysis are provided to business users, enabling these stakeholders to answer their questions and make data-informed decisions. Data modeling techniques. Inman characterizes the data warehouse using the following principles. Subject-oriented, the warehouse's data organization ensures that all data elements associated with the same real-world event or object are interconnected. Time-variant, modifications to the data in the database are tracked and recorded, allowing for the generation of reports that depict changes over a specified timeline. Non-volatile, data within the data warehouse remain unchanged and are never removed. Once committed, the data transforms into a static, read-only state, preserved for future reporting purposes. Integrated, the database incorporates data from a majority, if not all, of an organization's operational applications, guaranteeing the consistency of this data. Challenges in transforming data. Transforming data can be expensive and resource-intensive. This high effort-to-value ratio is due to a tension between data collection and analytics applications. For instance, your customer service software may fit the needs of the customer support team but stores data in a format unsuitable for analytics. The end goal must be clear. How will these data be used down the line? This may seem trivial, but it poses a real challenge. The considerations arising from the data transformation process will kickstart discussions among teams around key performance indicators, KPIs, and business rules. If those are not anticipated, the data team risks rewriting transformation pipelines to accommodate many changes along the way or managing conflicting views on how metrics are defined, resulting in multiple sources of truth. To assess the level of consensus, consider the following. Do stakeholders agree on common business rules? Are these documented? How well defined and mature are the use cases? Data enrichment. Data enrichment enhances data by incorporating additional information or attributes relevant to the business, enabling actionable insight and data-driven decision-making. The last steps of preparing ready-to-use data involve the following. Aggregate. In this step, you can summarize or group your data based on specific attributes or dimensions that provide the level of granularity relevant to your business stakeholders. Although aggregating will limit flexibility and the functionalities within your BI tool, it will improve performance depending on the volume of data exposed. Aggregations can be time-based, daily, weekly, or quarterly, location-based, by country or region, or grouped on any kind of dimension relevant to your analysis, product category, marketing channel, and customer type. Apply business rules. To support decision-making, data exposed in dashboards, analyses, or models should incorporate the following business rules. Filter certain records, for instance, excluding outliers or irrelevant fields. Incorporate domain-specific constraints and apply custom categorizations. Certain metrics can be calculated and materialized before serving them in your BI tools, such as revenue after taxes. At this stage, consider applying cosmetic renaming, reshaping, such as pivoting, or date formatting. However, be critical about whether these should be materialized or can be done in a BI tool. Avoid creating multiple versions of the same table that will serve a single dashboard each. As much as possible, apply transformations that result in a table that can be reused across many dashboards. For instance, if a stakeholder asks to rename all fields to a different language to accommodate a single user, do so directly in your dashboard. Augment. Enriching data may also involve denormalization, that is, merging tables. Whether or not you should denormalize your data depends on the volume of data and how it will be served. If certain analytics applications or services need to be able to retrieve data quickly, you might consider denormalizing. For instance, if a customer service analyst needs to regularly query data to retrieve customer orders and details, consider bringing together the facts and dimensions. On the other hand, if product information and order quantities are exposed, transforming data 102 through a BI dashboard, depending on the tool, it may be wiser to keep them normalized and to create relationships within the tool itself. For example, Power BI manages the relationships between tables in the Modeling tab of the tool. Other enrichment techniques include splitting long fields into multiple columns, such as extracting URL substrings with regular expressions. You have probably heard it said that data is the new oil. What most experts neglect to mention is that data is a costly asset that is only valuable for two things: automating processes and informing your users' decision-making. In other words, data only becomes useful when you serve it. Drilling down refers to navigating from a high-level summary to a more detailed view, for example, breaking down the data by year or by month. What-if scenarios involves changing variables or inputs to simulate outcomes. A typical example is, will we hit our target if we sell 3 more units per day? Dynamic window calculations allows users to analyze trends and patterns over time and aggregate data over a specific window of time, e.g., the last 30 days or 1 year ago. The most common examples are the moving average and running sum. Alerts, events or notifications are triggered when certain conditions are met or data hits a specific threshold. Examples are: send me a message if a client makes a purchase above 10K, or email me if a delivery takes more than 10 days. Most of the data system and platform implementations are software and technology specific. That means it is over 80% about hands-on experience and generating your own data to use with it. Data governance can be irresponsibly defined as everything you need to do to ensure data is compliant, secure, accurate, available, and valuable. Here are some examples of things that you, as an analytics engineer, can do to help. Prioritize code readability. It is okay if your code is less efficient and sophisticated as long as it is easy to understand. Avoid boilerplate code. Leave comments explaining the why behind some of your decisions. Use descriptive names for your variables and functions, and break your code into functions. Automate documentation. Very few people document their work, and even fewer keep documentation up to date. You can alleviate this problem with automation, from LLMs and other AI solutions that can explain how code works to tools that make documentation easier, e.g., dbt. Reduce technical debt. Spend time improving and refactoring legacy solutions. It might seem like a waste of time, but just know that this type of work happens anyway when something breaks. Regardless of when you do it, refactoring your business-critical data products pays off exponentially in terms of maintainability. Organizations also have a role in improving the transfer of ownership. You can convince your team and management to implement the following solutions. Force collaboration, make an effort to break silos. If you have a team of specialists, taking over each other's work is harder. However, if you force the team to work together on the same data products, they will understand each other's work more efficiently. You can accomplish this by conducting periodic initiatives such as code reviews, pair programming, or knowledge sharing sessions. Hire a data owner. Officially appointing a data owner as a full-time or part-time job is becoming increasingly popular. For larger deployments, it is also common to see domain owners, e.g., finance data owner or marketing data owner, or system owners, e.g., data laker owner or CRM data owner. To get better at data analytics engineering and building data-intensive platforms, it is easiest to pick one of the many public datasets and experiment with them by trying to build a system for them. You are likely to gain experience that way. That is all.